Welcome to According to Pete for the beginning of January 2018. I know this is going to go live on the 2nd, and right now I think we're the 17th? 17th today. So, welcome. I found myself thinking about overclocking an Arduino, like a standard 328. And it's been done, right? And I read up on it, and it looks like the fastest that anybody's been able to do is like 59 megahertz with some kind of crazy cooling mechanism. And then I found myself thinking, what if you went the other way? What would that look like? So today, folks, what we're gonna do is we're gonna clock it down. And this is the victim, our standard Pro Mini. I think it's a 5 volt, 3 volt, 5 volt, really doesn't mini. And really the whole point here, we're just gonna clock it down. We're gonna watch some clock signals. We're gonna play with an alternate clock signal and see how that works. And maybe we'll learn something along the way, right? Now, big disclaimer, I'm breaking all sorts of rules doing this. I'm not setting any clock bits. All I'm doing, literally, I'm yanking off the resonator on the Pro Mini and I am replacing it with an external clock, specifically a signal generator, and I'm just gonna clock it down and we're gonna watch what happens, right? Now, I understand that all of the peripherals that we would depend on, communication, maybe ADC, any number of other things are entirely clock dependent. So when you do this, there's really no practical use for it that I can imagine at all, besides power savings, but then it gets more complicated because you think you want it to run well at that frequency, and this will not. We're just gonna clock it down and we're gonna watch what happens. All right, let's get to it. So the first thing you wanna do before you start mucking up the hardware, which we're totally gonna do, is you want to characterize the clock signal. You want to see what it is that we're going to try to duplicate in order to get this thing to run, right? First thing we want to do is yank off the resonator that's on the board and replace it with another signal, an external clock, okay? So what we're looking at, if you just probe the crystal or the pins on the part, which is pin 7 and pin 8, what you're going to see is a sine wave, roughly a sine wave, not a totally good sine wave, but a sine-ish wave that runs from 0.4 volts to 1.1 volts at a frequency, my scope says, 15.9 megahertz. Now, excuse me, a couple of things you need to know if you haven't figured it out already. The scope probe is almost certainly loading the crystal, okay? So what I expect that result to be is maybe this waveform is going to shift a little bit, and certainly the frequency is going to shift a little bit. So this is not a surprising number. I'm not going to duplicate that, but I am going to duplicate this. So when we start this, I'm going to yank that resonator, and I'm going to replace its signal with 0.4 to 1.1 at 16 megahertz. All right, now let's talk about the hardware. All right, so to set this up, should anyone want to do this, the first thing you want to do is you want to program your Pro Mini. Before you go yanking off a resonator, you want to program it with something. Now, realizing that what we're going to do, as I mentioned earlier, is going to completely jack up most of the functionality that you might want out of a microcontroller, we really can't ask very much of it to do this test. So, program it with blink, and we will just watch those clock signals go by. The next thing you want to do is you want to yank off the resonator, all right? You want to make sure blink functions first. Make sure it does. Then you want to yank the resonator. We're digging in now. So, the resonator is this guy. I've drawn something of a scale, hopefully you can see that well, with the reset button at the top, the processor in the middle. The resonator is going to be this guy, the silver can there just to the right of the processor. And the way that you do this, right, you take your iron and you kind of lay it down sideways next to that can, and you get solder along the whole thing of it, and you get kind of like that. It only takes a couple of seconds, comes right off. And if you do it in the direction away from the processor, you won't get any schmutz on your processor pins. Works out pretty well. So after you get that off, you want to get your signal generator and you want to get your lines in on that pad. Now the signal generator that I've got is a Tektronix AFG 1022, nice signal generator. It's good to about 25 megahertz in sine wave, which is the opposite direction that we're going. I can't think of a signal generator that won't work at a low frequency. I could have set this up with a 555 pretty easily, I think. But get your signal generator. Now what you want to do is you want to put your ground, this is the pad for the resonator, okay? You want to put your ground on the middle one, and you want to put your signal on the lower one. This is crystal 1 and pin 7? Man, I hope I'm saying that right. I checked it before this. I wrote it down somewhere. I think it's pin 7. Double check the schematic. That's where you want your signal to go in, okay? And you want to set it to what we said before, 0.04 volts to 1.1 volts at 16 megahertz, right? And the very first thing you want to do is you want to turn everything on, powered up, have that clock going, and make sure that you're still running blink. It's still working, okay? And in fact, at this point, probably at the program bit, take out the delays, okay? So the program that I'm running, and I'll mention this a little bit more in a sec, is actually just digital write up, digital write down. Delays are completely removed, and the loop is still the main loop, okay? And we'll alter that as we go. You want to set up your scope probes. You want to watch the clock, and you want to watch the LED line, D13, all right? And once you got all that stuff set up, you start dialing it down, all right? Now let's look and see what happens. All right, now going into this, I want to make one more disclaimer. I realize how many rules I'm breaking here, right? If you look at the data sheet for the clock section, it will tell you unequivocally, do not do what I'm doing. It won't run reliably, right? In fact, it specifies you can't change the clock more than 2% between one clock pulse to the next, which I don't know if I'm actually doing it like that. I'm altering it willy-nilly. Now, when they say reliability, they're talking about like, you know, your communications are gonna fail, your ADCs are gonna fail, everything else is doing, we're not asking it to do anything special. All we're trying to do is toggle the line and watch what it does, all right? So, going into that, now we dial it down. So what I have here on my scope, I've got the clock signal on the bottom, which should just look like a bunch of fuzz to you because it's all crammed together. What I have on the top is the D13 line. So that's the LED line. And we are still running at 16 megahertz. So let's start to dial it down. And what I'm gonna do is just slowly, oop, that's the wrong way. So now we're at 10 megahertz. Shift my decimal. Oops, don't want to do that. I'll go faster. 52.1 megahertz. Change the time base on my scope. Move it again and dial it down to 100 kilohertz. And as you can see, got our clock here. We still got our signal here. Looks like it might be starting to get a little glitchy, but you know, we could be missing a trigger here or there. A little more, and 40, 30, 20, 10, and change our time base. So at 10 kilohertz, we're still going. I guess I'll leave that. 10 kilohertz, now 8, 7, 6, 5, 4. Now for dramatic effect, not that one. I'm gonna hold here. If you can see the square wave a little bit, the digital line, you can see it's starting to do this sort of thing, right? What's going on? And in fact, if I go a whole lot lower than that, 3.876, and you're gonna start to see blinky on the LED that starts to become erratic. The reason this is getting real sketchy at about 3.4 kilohertz, the frequency isn't nearly as critical as the understanding of why this is happening. And the reason is because we've taken the clock signal, which was a fairly tight signal I mean, it was a sine wave, but it's still a very fast sine wave. So the rise time and the fall time are fairly well predictable. And what we've done by decreasing that frequency dramatically is we've spread out that slope really crazy-like, right? And so the internal clock circuit to the processor can't find that edge. There is no edge. So, quick and easy fix, what we do is we go to a square wave. And now you see the blinking is fairly steady. Now we can dial it down much farther. All right, so now I've got it dialed down to 1 hertz. And what you're gonna see here, right, I've had to dial the scope way down so you can see this junk. At the bottom is the clock signal, very slowly going 1 hertz. At the top is the diode line, D13. And while I'm talking here, you're gonna see this thing go high periodically and then go low. But the first thing you realize is that the blink sketch takes a really long time to do at this frequency, which should be absolutely no surprise. We'll talk about that in a sec. It just went high, check it. Now, what do we find as far as performance at this frequency? Well, stupid things, really. I mean, okay, everybody says like, oh, if you want to get the best low current ability, you got to dial down your frequency. Well, a current measurement on this apparatus is almost meaningless. And the reason is because there are bunches of parasitic items on the Pro Mini board that are sucking current anyway, right? You've got quiescent currents out of your regulator. You've got leakage current in your caps. There's a power LED that's drawing X number of milliamps. So it's not really meaningful to dial back the current on the processor itself and try to take a measurement of that, because if we were going to do that, we would have set this circuit up from the very beginning to optimize that, and we have optimized nothing. This is just to see what happens, right? So once you get this frequency dialed down, and you start playing with the code, and you start watching how it works, it gets kind of interesting, right? And none of this will come as a surprise to anyone. And a lot of what I'm looking at right now are stupid compiler tricks, right? This is behavior you can look at any frequency, but it becomes really stark and glaring when you get to this frequency and you actually you count the clocks to get something done. So the first thing you find is that when you're running blink, and like I said, I have pulled out the delays. So all I have is digital write up, digital write down, and then it loops, okay? And what I've found is that it takes, wait, I wrote it down, 110 seconds for it to complete one loop. That's 110 clock cycles. It takes 54 for the up, and then 56 for the down, and then it repeats. And that's including the loop time, right? What is going on in that much time, man? What does it take? But that's what you find, okay? So then you go, well, I can shorten that up. So what I did was I went to port B equals, right? Or actually, port B or equals the full number, and port B and equals the other, just to get the toggle, okay? And then using the main loop. And doing that, you get it down, three clocks up and 6 clocks down when it goes through the loop. That's a dramatic difference. But again, this is not stuff that is particular to the component itself running at this frequency. These are compiler tricks. But it's really interesting to watch, so I wanted to bring that out. Now, the last thing I did in that regard, actually I've done a whole bunch of things, but the last thing I'll tell you about is that I put the two port B lines inside of a while one loop. So instead of using the main loop, I'm using a while one loop. So it's a very tight piece of C code. And what I find there is that I get 3 clocks for the up and then 4 clocks for the down. So I've tightened it up a little bit. And that's pretty good, right? I mean, I don't think you could expect better behavior out of that if you went to pure assembly, which we don't have to do, obviously. But these are just compiler tricks, and I wanted to bring it up because it's fun to watch it happen, right? But then it gets really interesting. So ultimately, the part fails. It stops running code, to say. Now, of course, if I spin the frequency back up and hit reset, it comes right back up, not a problem. But what failed? What failed at 1 hertz? Who knows? We haven't set the clock up properly. It could be failing anywhere. So I talked to some people, right? And started with, I talked to Marshall in passing. I'm like, hey man, I'm doing this thing and it quits. And he's like, oh, memory refresh. It probably takes a memory refresh. Well, turns out no. The Atmega 328 actually uses SRAM, static RAM. So it does not need a clocked refresh. It will maintain its state as long as it holds power. So it's not a memory refresh thing. And that kind of plays out as we go, and I'll tell you about that in a sec. The next person I talked to was Bob Martin at Atmel/Microchip. So Bob is like our go-to guru for everything Atmel processors. So I emailed Bob, like, Bob, this is doing this thing. I'm doing this test. I'm gonna fool around with this thing. What do you think? It's failing. And the first thing he said was, well, down at that frequency, you might have jitter issues and rise time, yada, yada, yada. And I said, but Bob, my signal generator says that specifies in the datasheet that it has a rise time of less than 12 nanoseconds and a jitter number of less than 1 nanosecond. So if it were that problem, if it were a rise time or jitter problem, we would still see that at 16 megahertz and everything else. We don't. To which Bob said, you have a point there. And he was going to go off and find out, but he hasn't got back to me yet at the time of this filming. So, I expanded the testing a little bit, right? What actually happens at 1 hertz after X number of minutes, and I don't have a specific number, but it's somewhere around 20 to 30 minutes, it just stops running code, okay? So then I dial it up to 10 hertz and I watch it again. Same thing, somewhere between 20 and 30 minutes, it'll stop running code again. And at 100 hertz, same thing. And now I didn't specifically time how long it takes, right? I hadn't gotten to that level of testing yet. All I have is fail, fail, and fail. Then I went to 1 kilohertz, and that's where something sort of interesting happens. At 1 kilohertz, at an interval of 16-ish seconds, what will happen is the LED, after like a period of 16 seconds, the LED will go full bright for a second and then it'll resume clocking. You can see it on the scope, but more than that, you can just see the LED go full bright, right? Because it's a PWM signal effectively. And so when it goes full bright, it's like, okay, it stopped oscillating right there, or something has happened. So, but the next time through, the next 16 seconds, what it will do is go full dark for a split second, and then it will resume again, okay? And so, but what I found is after a while, that ultimately quits too. Now, if I had to guess, and I didn't see it because I wasn't able to just watch the thing, and I don't have a complicated test apparatus set up, but it would be my guess that at that particular interval is where it's going to quit. It looks very quit, right about there. Now, other clues, 16-ish seconds at 1 kilohertz. 2 to the 14 is like 16,384. Is that a clue as to what's failing? I'm not really sure. But something else to mention is that over 3 orders of magnitude, and maybe we're just starting to see the edge of it here, but I would expect at 3 orders of magnitude, whatever's making it fail here would make it fail a lot less here and a lot less here and never here. But I could be wrong. I don't know. So this is where I'm at. This is the state of my situation. Now, I will never, ever, ever, probably, set this up someplace to do an actual thing. I've got no use for, I can set this up with a 555 or any other low frequency oscillator circuit to just toggle a line, okay? The point of a microcontroller is that it gives you all this other functionality like communication and you know, reading things, ADC, those are the things you want, right? And to do that, you need a stable and fast clock. And the faster the clock is, the happier everything's going to be. So there's not a whole lot of practical application for this, but it's really interesting to watch where it's going to fail. And Bob hasn't got back to me, like I said. This is the state. So for you, dear watcher, what do you think is failing, right? Is it in the clock settings? I didn't set anything different than the default clock settings. Is it a refresh? Is there a register that needs a clock refresh? Perhaps it's forgetting, but even if that were the case, you would expect that over these ranges, that would go away a lot sooner. So you tell me, where are we failing? So that's it. Thanks for tuning in. Happy New Year to everybody. Hope you had a good one. Hope you didn't get too into your holiday, as it were. Thanks for indulging me in all of this, and hopefully you've got some ideas about what this issue could possibly be. Again, I fully admit there's nothing practical about this. This is just for fun, and I want to see what's breaking. So until next time, if you have any questions or comments, put them in the comment section below. And I'll see you in about a month. Bye.